Hi scholars, today is Tuesday, October 27th of 2020, and our lesson is 3.1.1, Waves 101. So this is going to be sort of like Waves basics. For your do now, you will answer these two questions. Number one, imagine you have to teach a crowd how to do the wave, as seen in this image to the right. Write out the instructions that you would give the crowd. And then number two, what are some examples of waves that you have seen before? Our three objectives for today's lesson are: first, Knights will be able to define waves. Second, Knights will be able to label the parts of a wave. And third, Knights will be able to define the frequency and amplitude of a wave. So let's go back to some of the examples of waves that you may have written down for your do now. So of course, this is one example of a wave, but we also have waves in the ocean. They could also be called tidal waves. We have sound waves. We have heat and light waves, among many, many, many other types of waves that are not given here. Now, all of these waves have the same things in common. So any wave is just a disturbance that transfers energy from one point to another without transferring matter. So essentially, matter has just kind of its own typical behavior, and that behavior is interrupted when energy travels through it. So anytime that energy is traveling from one point to another, whether that be from the sun to earth or from my vocal cords to your ears, it does so in the form of waves. So for example, what happens when you drop a rock or a stone or nuts like these into a body of water? Like shown in this image, you get a splash, of course, but after that, ripples will also appear in the surface of the water. And those are waves that are traveling outwards in all directions. So we know that when you drop that object into water, it has kinetic energy, and we know that because it's moving. Therefore, when that object hits the surface of the water, some of that energy is transferred into the water. And the energy, of course, travels from that point of impact, the place where the object hit the surface, outward in all directions, which, as that energy travels outward, energy traveling must be in the form of waves, and so it creates waves that move away from that point in all directions. And that's why it looks like a little circle. Ripples are just energy traveling from one point to another. What are some other examples of energy traveling from one point to another? Maybe you're thinking of like heat from a campfire. That's energy. It travels from the campfire to your skin so you can feel it. That travels in waves. Or like I said before, light energy from the sun travels all the way to earth. That travels in waves. Sound is energy, which travels in waves. So waves often have to travel through matter. Not always, but often. And whatever matter that a wave travels through or whatever matter carries that wave is called the medium. So, for example, the sound energy that's coming from my body is traveling through air. So, in that case, the medium of that wave would be air. The ripples on the surface of the water, as shown in this animation or this graphic, those waves are traveling through water, and so the medium is water. So when a wave does travel through a medium or matter, the particles, the atoms or molecules that make it up, they do move, but they don't actually travel. So before we look at that, we need to think about the difference between moving and traveling. When I'm teaching, I move a lot. I talk with my hands, my body moves, my hair moves, but I'm not actually traveling because I'm not leaving my chair. I'm not going from point A to point B, even though I am moving. Think back to the example of the wave traveling through the crowd, like at a soccer stadium. While the people are moving, you have to stand up and sit back down, raise your arms and put them back down. They're not actually traveling. Nobody is running from one end of the stadium to the other, just like the matter that carries a wave. So let's look at some examples. In this one, you could pick any of these points and track its movement. So the red ones are highlighted just so that we can see them a little bit better. So let's watch one of those red ones. And I'm going to draw a line that shows its path of travel. Notice how that particle just moves up and down along the same line. And I could pick a black one, and it will do the same thing. This particle just moves up and down along the same line. These particles are moving, but they are not traveling. We can, however, see that something is traveling. If you watch these little blue tick marks, they're definitely traveling from left to right. They start at the left and they move all the way to the right. That, however, is not matter. It's energy. Energy travels from one point to another. The matter, though, is only moving in place. Let's look at another example. Let me erase these. Here's just another type of wave. And again, we can pick any of these particles. The red ones are highlighted so that you can see them a little bit better. And just observe their motion. In this case, the particles are moving slightly side to side, horizontally. And again, I could pick any of the black ones too, and it would do the same thing. It's just moving side to side in the same place, in the same position, I guess you could say. Now we can see that something is moving. We can follow the waves as they travel from left to right. However, the only thing that's actually traveling is the energy. The matter, on the other hand, is just moving slightly in place. I have one more example for you. Let me erase these marks. And the example that I have is called surface waves, and these are waves that travel across the surface of water. In this one, again, we can clearly see the energy traveling from left to right on the surface of the water. But if we focus in on the particles, the water molecules that make it up, they do not travel from left to right. They simply move in circles in place. Now, the ones that are closest to the surface will move the most, and the further down you get, the less the particles will move. However, none of these particles are actually traveling through the water as a result of these waves. So let's talk about the different parts of a wave. All waves can be represented mathematically. That basically means that they could be graphed. And this is what they look like when they're graphed. Now, waves don't actually look like this in real life. In fact, we can't see most waves. However, we can put them on a graph. And when we do so, there are different parts of the wave that we use to learn more about it. So the first part we'll talk about is called the resting point. And this is where the medium is, the position of the medium in the absence of energy. And that's what that straight line across the middle describes. This is where the medium is when there's no energy moving through it. So you can picture a calm lake or pond. There's no wind, there's no storm, there's no rain, there's no boats. The surface is perfectly still. All of that water, all those water molecules are at their resting point. However, as soon as energy starts to travel through it, waves will be formed. But without the waves, that matter is at its resting point. Then we have what's called the crest of a wave, and this is its highest point. So these are 3 individual waves and 3 individual crests. Then we have the lowest point, that's called the trough. And here we have 3 individual troughs because we have 3 individual waves. Now let's talk about what makes one full wave. That would be called the wavelength. The wavelength is the distance between the same point on 2 adjacent waves, or it could be described as the length of one full wave. Now, one full wave is going to have one up and one down. So here, this line marks the first wave in this sequence. And it goes from the resting point at the very beginning of that wave to the resting point at the end of that wave. And like I said, each wave has one up and one down, one crest and one trough. However, sometimes this distance is hard to measure. You can also measure the wavelength by measuring from trough to trough, or you can measure the wavelength by measuring from crest to crest. In fact, you could do any random point along 2 waves that are next to each other. The easiest ones, though, to find, I would say, are between crests or between troughs. And then we have the amplitude of a wave. And this is the distance between the resting point and the crest, like this. Or it could be the distance between the resting point and the trough, like this. Typically, those are the same distance, and so we could use either one to measure the amplitude of a wave. And the last part is the frequency. That's one more thing that we can describe about a wave to learn more about it. And so it has everything to do with its wavelength. So real quick, let's review which of these waves has the longest wavelength. Well, like I said before, I personally like to look at the crests or the troughs just because it's easiest to find. So I'm going to draw a line between these 2 crests that are next to each other. That's the wavelength. I'll go ahead and do it for all of these waves so then I can compare. Whoops, that one's a little bit long. Okay, so if I'm looking at these waves, I'm just looking to see which one has the longest wavelength, which is going to be A, because these waves are much farther apart than any of these others, but especially like, for example, E, much farther apart than these waves. The length of this wave is much longer than the rest of the waves, and so that has the longest wavelength. So the red wave, again, it had the longest wavelength. It also has the lowest frequency. So if we think about the term frequency, just outside of science, outside of waves, we're talking about how often something happens. If I ask you, how frequently do you go to the gym? I want to know, how often are you going? Maybe you go 3 times a week. That's the frequency with which you go to the gym. So when we're talking about waves, it also is measuring how often, but this time it's measuring how often a wave passes, specifically within a certain amount of time. So the frequency of a wave measures how many waves pass per second. So we can also call that waves per second, and the unit that measures waves per second is hertz. So if I have 3 waves passing in 1 second, that's 3 hertz. If I have 2 waves passing in 1 second, that's 2 hertz. If I have 27 waves passing in 1 second, that's 27 hertz. So again, if we look at this diagram, let's say that this box represents 1 second. Which one of these has the highest frequency? The one with the highest frequency is going to be the one on the bottom. It's pink or purple or whatever. And that one has the highest frequency because it has the most waves passing within that 1 second. You may notice it also has the shortest wavelength. The shorter the wavelength a wave has, the higher its frequency. And the longer the wavelength, the lower the frequency. So that's all for today. Please reach out if you need help or have questions. You can reach me probably best and easiest by Hangouts. And I hope you all have a great day.